In our last project, we did the impossible. We slashed the ESP32's power usage by 99%, hitting the holy grail of 5 microamps in deep sleep. But I cheated. I had a factory assemble that board. Today, I'm doing it the hard way. We are building the V2 Barebones Mini, a custom 4-layer dual-mode IoT module completely by hand. Stencils, reflow, and shaky hands included. Can we beat the factory? Let's find out. But real quick, I'm just one guy in a shed sharing what I learn. If you enjoy seeing these experiments, please hit that like and subscribe button. It genuinely helps the channel survive and tells me this is the content you want. I promise I read your feedback, and I'm incorporating it right now. So thank you for being part of this. It means the world. Standard dev boards are vampires. They have voltage regulators, USB chips, and LEDs that suck your battery dry even when the code tells them to sleep. Last time, we fixed this by removing everything. Addition by subtraction. But that created a new problem. Without a regulator, you can't use a standard LiPo battery. 4.2 volts will fry the chip instantly. We were stuck using only LiPo for batteries. Enter version 2, I've added a dual-mode power topology. Flip the switch one way, regulated mode. The power goes through a low dropout regulator. Now you can safely use standard LiPos or USB power. Flip it the other way, direct mode. We bypass the regulator entirely. This connects a 3.2 volt LiPo 4 battery straight to the chip's vanes. No regulator, no quiescent current, maximum battery life. Warning, in direct mode, there is no protection. If you plug in a 4.2 volt LiPo while in direct mode, you will fry the chip. Check your voltages. We're designing this in KiCad. I've put the full schematic and project files on GitHub. Scan this QR code or check the description to grab them for free. We're using a 4-layer Stackup. Signal on top, ground and power planes in the middle, signal on bottom. This internal shielding is critical for RF performance. And speaking of RF, notice how the antenna area hangs off the edge? That is intentional. You never want ground planes under a PCB antenna, or your Wi-Fi range will be 0. But I also designed this layout to be antenna agnostic. It fits the standard chip with the built-in antenna, or the 1U variant with the tiny IPEX connector. This means if I need to put this project inside a metal box later, I just swap the chip, snap on an external antenna, and we're good to go. One design, infinite use cases. And see these half circles on the edge? These are castellated holes. It lets us solder this entire board onto another board later, turning this into a plug-and-play IoT module. Tip: set the center ground pad to thermal relief, not solid. If it's solid, the copper plane will suck all the heat away during soldering, and you'll get a cold joint. Thermal reliefs are a lifesaver for hand assembly. Designing is half the battle. Manufacturing is the other half. This project is sponsored by PCBWay, and I'm going to show you exactly how to order this so it's easy to assemble. I used the PCBWay KiCad plugin to generate my files in one click. On the order page, since we have those cool edge connectors, make sure you select castellated holes. Now, here is the secret to easy soldering, the stencil. I added a stencil to my order. I ordered a framed stencil. It's huge and great for machines, but for a small desk, it's overkill. Save money and desk space. Order the unframed version. Also, check the box for electropolishing. It smooths the stencil walls so the solder paste releases perfectly on these tiny pads. To make the most of the shipping, I also picked up some essential tools from their shop. A proper SMT squeegee, some high-quality ESD tweezers, you'll see why in a second, and a roll of 4.8mm flux core solder. The boards arrive looking incredible. Check out the link in the description to get a $5 credit on your first order with PCBWay. Time to build. Step 1, the undertape wings method. I tape the board to the desk, then tape scrap PCBs of the same thickness around it. This creates a flat floor so the stencil doesn't bow. Align the stencil, apply the paste, and swipe. You want one clean pass. Look at that definition. That is the power of an electropolished stencil. Step 2, pick and place. I don't have surgeon hands. My hands can shake. If yours do too, here's the hack. The pinky anchor. Never float your hand. Anchor your pinky on the table and pivot your fingers. And breathe out when you place the part. I'm using 0805 size components. They are small, but big enough to handle with tweezers. Smaller 0402s can be more difficult. For the ESP32, tweezers are risky. I use a cheap vacuum pen. Technique: use the pen to drop it near the pads. Don't try to align it perfectly. Drop it, release the vacuum, then use tweezers to nudge it into place. Check the top left corner, then the bottom right. If the diagonals align, the whole chip aligns. A lot of tutorials tell you to solder the plastic bits, like connectors and switches, by hand later, so you don't melt them. Forget that. These are quality SMD components. They are designed to survive the heat of a Reflow oven. So I'm placing everything right now: the slide switch, the boot and reset buttons, the battery connector, and the programming header. It saves me 20 minutes of manual soldering later. Step 3. The heat. I'm using a hot plate set to 240 degrees Celsius. I place the PCB on a carrier board, a spare piece of copper, so I can move it without bumping the parts. Watch closely. First, the flux activates. It looks wet. Then, the small parts turn shiny silver. Finally, the big ESP32 will settle. Once it flows, let it soak for 15 seconds. We need that heat to penetrate the 4-layer Stackup and melt the ground pad underneath the chip. Normally, you would slide the board off to cool it down quickly. Me? I was too scared. If I nudge this board while the solder is still liquid, the components will slide everywhere and it's game over. So I just turned the plate off and let it cool down naturally. It takes longer, but it guarantees zero vibration and zero mistakes. Inspection time. I'm looking for bridges. 2 pins connected by accident. The stencil did its job perfectly here. Before we apply power, we do the smoke test. Mode, continuity, beep. Test 1, ground to ground. Beep, good. Test 2, 3.3 V to ground. Silence, good. Since we removed the USB chip, we need an FTDI adapter to program it. RX to TX, TX to RX. Hold boot, tap reset, release boot. We are in download mode. I uploaded the data logging sketch from my previous video and boom, it's connecting to Wi-Fi and logging data. The antenna design works. Now, the numbers. Did we beat the 5 microamps? I've got a Nordic Power Profiler 2 hooked up. Test 1, old V1 prototype. It averaged about 7.4 microamps. Test 2, new V2 in regulated mode, LiPo. Result, 16 microamps. Why higher? That's the cost of the LDO regulator. It burns current just to stay awake. It's convenient, but it costs power. Test 3, new V2 in direct mode, LiPo 4. The regulator is bypassed. We are running raw. The result, 9.1 microamps. We missed the 5 UA goal by a hair. But why? Even when bypassed, the regulator chip leaks a tiny amount of current, about 1.7 microamps, through its internal feedback resistors. Think of that extra 2 microamps as a versatility tax. The V1 board was a one-trick pony. It had great stats, but if you plugged in the wrong battery, it died. This V2 board is a Swiss Army knife. We are deliberately paying that tiny current penalty. In exchange, we get a robust 4-layer module that handles any battery chemistry and integrates into any project. That was a deliberate engineering choice, and for a board that can still run for years on a single charge, I will take that trade-off. We did it. We designed, sourced, and hand-assembled a professional-grade IoT module. If you want to build this exact board, I've shared the PCBWay project link in the description. You can order the PCB, the stencil, and the parts and build it yourself. If this felt fast, I have a massive companion article on my website with every step, the code, and the full bill of materials. Check the link below. What should we build with this module? A solar weather station? A mailbox sensor? Let me know in the comments. Thanks to PCBWay for sponsoring, and I'll see you in the next build.